Hello and welcome to today's webinar. I'm going to introduce slowly while we're waiting for the participants to join in. So today's webinar is the third webinar in the FlexSNG series. Today we'll be hearing from Sana Toomey, Ilka Hiltman and Sri Wenshra Swikumar from Sumitomo. And today our lovely three presenters will be presenting about the flexible gasification process, which is the core of the FlexSNG project. So before we get going, just a few housekeeping rules for our participants. We welcome you to use the chat box for exactly that, for chatting. So please use this for welcoming yourself to the webinar, saying hello to your friends, or if you can't hear, etc. If you have a question, which we hope you do during the presentation, please write it in the box that says question and answers. These questions will be collected and either responded to in the written form during or after the webinar, or at the end of all the presentations, we hope to answer as many questions as possible in live. So please do use that box, because if you use the chat box for a question, it might be lost. Okay, good, excellent. So again, I'll welcome today's three presenters. We have Sana and Ilka from BTT and Shiri from Sumitomo. And as I said previously, this webinar is going to cover the FlexSNG process, the concept, the core of the development in biomass gasification, and how Sumitomo is helping with the upscaling. So without further ado, I'll hand over to our first presenter, who is Ilka. So Ilka, welcome.
Okay, thank you very much, Emma.
You're welcome.
And welcome to everybody. I will share my presentation. That would be maybe in interest of everybody. So, once again, and then duplicate. So, welcome on my behalf also to this FlexSNG webinar. And today the topic is flexible gasification process. And I'm Ilkka Hiltunen. I'm a research team leader of gasification and syngas processing at VTT. And about VTT itself. So VTT is a multi-technological research institute. We are located in Finland. We are a non-profit company, a research company owned by Finnish state. And we are pretty large. So we are almost 2,400 employees, but then distributed for different type of technologies. And mainly we do applied science. Gasification itself, it's a topic which VTT has been involved already quite a long time. And what gasification actually is, it's a conversion of carbon-containing material into gas which has heating value. In Finland, we don't have national resources like fossil resources. So we have at VTT, we have a concentrated whole time for biomass and waste gasification and conversion either to fuel gas, which can be utilized at industrial kilns or boilers, gas turbines, engines. So basically for heat and power generation. The 20 years I have been almost at VTT, we have mainly concentrated on synthesis gas production. So production of synthesis gas, which can be then utilized via different end synthesis for advanced transportation fuels or chemicals, hydrogen production. And as I already mentioned, so we have quite a long history. also in the synthesis gas field. So VTT was involved in the synthesis gas development already in the 1980s when there was a peat to ammonia plant built in Oulu. That was actually a high temperature Winkler technology, German technology, which was then applied coal gasifier for peat and wood. Then later on, early 2000, the interest for this technology raised, and VTT developed a concept which I will be present soon, and it's also then demonstrated with by industrial partners, which standard technology partner was Sumitomo SHI FW. And then lately we have focused on waste to syngas processes, trying to get the scale bit down and get the lower capex, and also utilization of renewable electricity together with this biomass and waste gasification, boosting the syngas processing with renewable hydrogen. The technology, which is actually basis of this FlexSNG concept also, is such that we have a circulating fluidized bed gasifier, which is a robust gasification technology developed for biomasses and wastes, which have a high volatile content. It's fluidized with steam and oxygen. So we don't have then the dilution of the nitrogen in the product gas. The fluidized bed gasifier is robust from the feeding point of view. So, and utilization of wide feedstock bases. There is no necessarity to make any like let's say pre-processing of the feedstocks. Bit, of course, particle size should be bit grinded, but it doesn't need any pyrolysis or such steps. But biomass can be used as such, and also quite fluffy materials and high alkali and ash content materials can be used. After the gasification, the product gas is filtered. So then we actually remove a lot of most of the alkali metals, heavy metals. Of course, if there is some char, grinded bed material from the gas, and after the filtration, we still have tars there left, and higher hydrocarbons. And VTT has developed then the reforming technology, catalytic reforming technology for decomposing these tars and benzene, methane, and maximize the yield of synthesis gas. Then the gas need to be still ultra cleaned from the catalyst poisons, and then the synthesis gas can be utilized at different synthesis. And today we are concentrating in this FlexSNG for synthetic natural gas production. But the basis of this technology, which we are further developing in this project, is actually quite mature already from the gasification point of view, as well as also from the synthesis part. VTT has excellent facilities for developing this gasification concept based on fluidized bed gasification, and this picture just illustrates that we have actually facilities from raw material until the synthesis end product. So from biomass and waste until Fischer drops. In this project, we have then the synthetic natural gas as where we are focusing. And this technology, as I mentioned, is this gasification technology in this project. It's already demonstrated in industrial scale. It was demonstrated by Neste and Stora Enso, which are Finnish-based companies, and then Sumitomo SHI FW was the technology deliverer and technology company for the gasification part there. So where we have built it, this gasification process of this FlexSNG, it's actually quite mature and something which can be already got from the industry. In FlexSNG project, we are then concentrating on flexible production of synthetic natural gas and biochar via this gasification process. This is an international cooperation with Canada. So we have a really great consortium from Europe and from Canada, both research organizations and then industrial partners, which are really focused on the development of this technology. The FlexSNG in brief, so basically we are developing a flexible and cost-effective gasification process to produce pipe quality biomethane, biochar, and then renewable heat. And where we are focusing from the raw material side is biomass residues and biogenic waste feedstocks. And we already had a webinar which concentrated on a feedstock supply chain, where we do optimization of this feedstock supply chain. Then today we concentrate on development of the gasification process. And then we have also the biomethane production here and the case studies, which is an important part of this project. In FlexSNG, we developed a flexible gasification process, which can either maximize the production of biomethane, which is the mode 2. So basically, in this maximized mode, we utilize the feedstock as efficiently as possible. We also have a wide feedstock basis by co-processing biochar and low quality waste feedstocks. And then in the other mode, the same process is then utilized for co-production of biomethane and biochar. And this is the flexibility which we are studying in this concept and project, and actually something which then Sanna Tuomi will have a more detailed presentation of what kind of studies we have done so far. So thank you from my behalf.
Thank you, Ilkka. That was a really good summary there. And as you quite rightly said, we're now going to hear from Sanna, who's going to tell us a bit more about the actual FlexSNG process. So over to you, Sanna, the floor is yours.
Thank you. Just a minute. Trying to share my screen here.
Yeah.
Yes,
we can see it all perfectly. Okay.
Great.
Thank you, Sanna.
All right. So good afternoon, everyone. So my name is Sanna Tuomi, and I work as a senior scientist at VTT, and I was previously actually coordinating this project. And I have been working at VTT for 15 years now with different gasification processes based on fluid aspect gasification of biomass and waste. But now I would like to discuss a bit of our some of the key findings from the gasification process development that we conducted as part of the FlexSNG project. So here, as Ilkka already mentioned, we have this gasification process where the target is to be able to, the process itself is capable of both co-producing good quality biochar that would have some end value, some use, for example, in soil amendment and so forth, but then also, of course, producing synthesis quality syngas. And then it should be able to switch to also maximize conversion of feedstock to syngas and then converting the syngas into the biomethane product in the end. But in the gasification process development here, we really primarily focused on the co-production aspect of this process, as it's the new feature for gasification processes. So typically, of course, a gasification process is typically adjusted so that the conversion of the feedstocks to syngas is maximized, but this time we restricted the carbon conversion to gas so as to produce also this solid carbon product on the side that can be then sold and used for different applications. And our first assumption when we were preparing this EU project proposal was that for this type of co-production of biochar, we would need some new type of fluid aspect gasifier, that a standard CFB gasifier, a circulating fluid aspect gasifier, or a standard bubbling fluid aspect gasifier would not be really the ideal solution. And here we have an image of a CFB gasifier. For example, in CFB reactor, the charcoal that is entrained here from the reactor, it's separated by a cyclone and then returned back to the bottom of the gasifier. And it's typically the entry point to the gasifier is close to the grate where the char actually comes in contact with the fluidizing oxygen. And this leads to really high carbon conversions. Of course, now that we have a target of producing also some solid carbon products, we would lower the gasification temperature, but still we have this conception that the product, the carbon product would be mainly entrained from the gasifier and then captured as filter dust. And as it ends up in the filter unit, it's really fine material. It's mixed with the bed material, and it would also contain some small amounts of polyaromatic hydrocarbons that we saw as complicating for considering the end use of the biochar product. And also when operating a CFB gasifier at lower temperatures, we would be producing more tars in the gas, and this would potentially block the filter unit and also cause some soot formation in the reformer. And therefore, we suggested this new type of gasifier, which is a BCFB gasifier. So a bubbling circulating fluid aspect gasifier, which is illustrated here. So it's a combination of a bubbling fluid aspect bottom part and a circulating fluid aspect top part. So the idea here was that the bed is operated at lower temperatures, and low fluidizing velocities are used at the bottom here, and the biochar product would be discharged from the process through the bottom of the reactor as bottom char, and then it would be separated from the bed material simply by sieving. And then in the upper part of the gasifier, we would use secondary steam and oxygen to increase the temperature and decompose some of the tars that would then facilitate stable filtration and reforming of the gas. And in this case, it's also essential that the cyclone that returns the charcoal back to the gasifier, the feeding point is to the upper part of the dense bed and not close to the grate where it would again come in contact with the fluidizing oxygen. So keeping these two gasifier designs in mind, We started the gasification process development in FlexSNG at the outset of the project in 2021 and 2022. We carried out altogether 3 one-week-long tests using this atmospheric pressure fluid aspect gasification unit, which is located at VTT's piloting center in Bioruukki. And we used 3 different feedstocks, which were straw pellets, wood pellets, as well as crushed bark pellets. And the focus was really on examining how these 2 alternative gasifier designs would be suited for co-producing good quality biochar. And from the process concept point of view, the focus was on the front-end gasification concept, not only on the gasification performance, but also how the gas can be easily cooled, filtered, and then reformed. And with catalytic reforming, we were partnering with our project partner, Johnson Matthey, that supplied us the reformer catalyst for testing. But then let's start with the experiences that we gained from the bubbling circulating fluid aspect gasifier. So on the left-hand side, we have the gasifier temperature depicted in one of our test campaigns. In red, we have the bed temperature, and in the blue line, we have the upper part or the freeboard temperature. And on the right-hand side, we have the distribution of feedstock carbon to gas, tars, and then the gray one is the solid product, the filter dust, and then pay attention to the red, which is the bottom char, which was really our target in this case. So this test campaign was started with high temperature gasification, so really maximizing the carbon conversion, and then gradually lowering the gasification temperature, so the bed temperature, but still maintaining fairly high temperature in the upper part of the gasifier in the attempt to really reduce the tar loading in the gas. And as we lower the gasification temperature, we can see in this figure that we increase the amount or the proportion of carbon that ends up in the solid products. But as we can see, it's still mostly captured as filter dust. So this was something that we quite quickly found out that most of the charcoal is actually ground to really fine dust due to attrition, and it's mainly captured as filter dust. But since we were really targeting at producing what we thought would be of more high quality biochar when we would recover it from the bottom of the gasifier, in this third bar here, this was a set point where we didn't have any external bed material in the gasifier. So the bed inventory itself, it was composed only of the biochar product itself. So in this case, we achieved the highest yield of bottom char, which really was the desired product. But on the other hand, when operating the gasifier without any external bed material, we could see that the operation was fairly unstable, as we typically have a mixture of sand and dolomite as bed materials. And then also it would complicate the switching between operation modes. It would be more time consuming as we would need to change the bed material in between. But on the positive side, we still could achieve this flexible operation. And also the secondary oxygen feeding method was found to lower the tar content in the gas so that the filter and the reformer operated well in all conditions. And the highest yield of biochar could be achieved at this temperature range, so below 700 degrees Celsius. And what was more encouraging was that the analysis results of the filter dust and the bottom ash derived char, they indicated that they were fairly similar in terms of quality. So they didn't have any significant differences. So therefore, this was really encouraging for really examining the standard CFB gasifier in the production of biochar. And that was done using bark and straw as feedstocks. And here we have again the feedstock carbon distribution to the gas, tars, and solid products being filter dust and bottom char. In this case, in contrast to the BCFB gasifier design, now we were trying to discharge the carbon product as filter dust, and we didn't use any secondary oxygen feeding to the freeboard. And here we can see the high temperature gasification point in comparison to the low temperature co-production point where we produced the biochar product on the site. And the same goes with straw. So overall, we could achieve this good stable operation in both operation modes, and we could easily transition between the two operation modes. And the biochar yield could be simply improved by reducing the gasification temperature. And also what was really important was that the filter and the reformer could really handle these high tar loads, and there was no indication of blocking or soot formation in any parts of the process. So to conclude, we saw that the standard CFB gasifier, it was capable of producing biochar which had sufficient quality for the end applications that we were targeting, and it could be achieved with a less complex and well-proven reactor design. So therefore, we selected the circulating fluid aspect gasification process for the validation test campaigns. So then we continue the development. So the validation test campaigns, they took place in last year and at the beginning of this year, using this 0.5 megawatt pressurized fluid aspect gasification pilot plant, which is illustrated here. So we conducted altogether 3 test campaigns that totaled up to 190 hours of operation under gasification conditions. Here we can see the feeding systems for the feedstock and the bed material. And then we have the CFB gasifier, the first gas cooler, the filter unit, the catalytic reformer, second gas cooler, and then the final gas cleaning train, after which the gas is suitable for Vesta methanation. And then we also had our project partner from Denmark, the Technical University of Denmark. They were working with oxygen transport membranes, this kind of new method for supplying oxygen to the gasification process. And this was tested in a slipstream of our pilot unit. And here we have pictures and compositions of the different feedstocks that we tested in our validation test campaigns. So ranging from really clean wood that is kind of a easy to handle feedstock with low ash, sulfur, and chlorine content, then typical woody residues, forest residue pellets, and also wood waste, and then straw pellets, representative of agrobiomass. And then the most challenging one was the solid recovered fuel pellets with the highest ash content and with high levels of both sulfur and chlorine in the feed. And then also we co-fed some biochar together with SRF in order to improve the gasification performance. Then a few words still about the filter performance and the catalytic reformer performance during the validation test campaigns. As Ilkka already mentioned, the purpose of the filter unit is to remove the particulates, heavy and alkali metals, and also most of the chlorine species. So we first cool down the gas to around 500 degrees Celsius so that we condense these species, and then we can remove them along with other particulates in the filter unit. So the raw gas enters the filter unit through this pipe. It's dispersed to the filter vessel. The gas goes through the porous filter elements. They are these candle type filter elements. We have these 1 meter long filters installed in the pilot unit. The dust accumulates on top of the filter elements, and then the clean gas goes through the porous filter candle and then exits the filter vessel from the top. And then we use nitrogen backpulsing to detach the dust from the filter surface, and then it's collected through the bottom here. And in this figure, we have the pressure difference, which is measured across the filter unit. And as we can see, throughout the test campaign, the pressure difference is really stable. Even the conditions where the gasification bed temperature is lower, which indicates that more tars are entering the filter unit. Still really stable operation, which would indicate that there is no filter blinding taking place, nor did we experience any filter breakages or leakages during testing. So overall, good performance throughout all the tests. And regarding the catalytic reformer, so the purpose of the reformer is, as Ilkka explained, to efficiently convert all tars, benzene and light hydrocarbons into carbon monoxide and hydrogen. And in this case, as we are targeting of producing SNG, we are really trying to minimize the reforming of methane. And in our pilot unit, we have this type of three-stage catalytic reformer, which is operated autothermally, which means that we are supplying oxygen mixed with nitrogen and or steam on top of these catalyst stages. And we use this type of nickel-based catalyst that were supplied to us by our partner, Johnson Matthey. Again, we have the reformer pressure differences plotted against time here. And as we can see, again, really stable operation. If there was an increase in the pressure drop, it would indicate that there is some soot formation or coating of the catalyst in some of the beds, but there is no indication of that. So really stable performance, even in this test run where we were operating the gasifier with solid recovered fuel mixed with wood pellets. So really high tar loads were entering the reformer unit here. As for the conversion levels, so the conversion of tars, benzene, and methane in the reformer, here are the levels illustrated for different feedstocks. So wood pellets, they represent a really low sulfur containing feedstock. Forest residues with slightly higher sulfur level in the feedstock. And then the most challenging one, the solid recovered fuel, which was mixed with wood pellets with really high sulfur concentrations. And overall, we achieved this good reformer performance in all conditions. And here we can see that especially with the low sulfur containing feedstocks, we really can reach full conversion of tars, and then maybe some minor breakthrough of tars with higher sulfur containing feedstocks. And also the benzene conversions were high, even up to 99.9, so almost full conversions were achievable, and that can be tuned by optimizing the reformer design as well as the operation parameters. For example, here we can see how the reformer outlet temperature affects the conversion levels. So the higher the temperature, the higher the conversions. And typically, and for example, with solid recovered fuel, to counteract the sulfur deactivation that takes place in the reformer, we typically need to increase the reforming temperature to keep the conversion levels at sufficiently high level. And then regarding the methane conversion levels, they were ranging between 40 to 80%. So lower conversions are achievable. This typically means lowering the reforming temperature, which then again leads to higher breakthrough of tars and benzene from the reformer. And in FlexSNG, we then ultimately made the choice of really optimizing and maximizing the conversion of tars and benzene, and although we were losing some of the end product, some of our methane with that. All right, I think that was the last slide from my side, and I will pass it on to you, Shri, from Sumitomo.
Thanks, Anna. Okay, we can.
Can you see my slides?
Yes, we can see and we can hear you. Over to you, Shri.
That's great. Okay. Hello, everyone. I'm Shri. I'm working as an R&D engineer in gasification technology at Sumitomo SHI FW, or SFW for short. And Let me begin by giving you an overview of SFW as a company. So SFW is a forefront of developing sustainable energy solutions with a mission to power a decarbonized world for everyone. Our global footprint is big. As you can see here, we have around 1,800 employees around the world working in over 20 locations. So with a history of around 130 years of experience, we are built mainly on innovation. And we have extensive experience and portfolio of over 800 successful references worldwide, particularly across the regions such as America, Europe, and Asia. So our dedication to integrated solutions and services is reflected in our 5 core values, which is from safety to respecting our people. So SFW is a part of Sumitomo Heavy Industry, which is a Japanese-based company, and we are in the line of energy and lifeline segments. So this segment alone contributes over 1,300 million euros annually to our diverse portfolio. So this is just to give you an overview of SFW. And as I discussed earlier, we have our offices and construction sales office all around 20 locations in the worldwide. And our head office is in Espoo, Finland, and our R&D centers are in Varkaus, Finland, and Niihama, Japan. And our list of references, meaning the customers whom we have served, are all across America, Europe, and Asia. We specialize in CFB boilers and scrubber technologies. And as you can see in the map here, we have delivered more than 40 gigawatt electrical of installed power capacity across the globe. Well, to address decarbonization and to mitigate climate change, we have organized our company into 5 technology lines, which includes the good old CFB boilers in energy generation, and also innovative upcoming technologies such as carbon capture, gasification, energy storage, and services. As we are involved in gasification in this project, I will be discussing more about this specific technology from here on. So if you would like to know more about our other technologies, please feel free to ask in the Q&A. So as Ilka explained earlier, gasification is a core technology where we convert biomass and recycled materials into sustainable syngases, which can be further used for the production of biofuels, chemicals, or value-added products. So our experience in gasification technology spans over 40 years with extensive testing and strong patent portfolio. So we have delivered around 11 commercial gasifiers as till date, and we have commercial readiness for around 200 megawatt. So as you all know, the market for gasification is expanding rapidly. Sustainable aviation fuels are critical, with the regulations in EU and internationally driving the need for net zero targets by 2050. On the other hand, we have methanol and biomethane as a key alternative for traditional fossil fuels. And also we have hydrogen, which is really upcoming, and all these new EU rules which are boosting hydrogen production. And also finally, we have these plastic recycling, which is also a major field of interest now. So we at SFW are focusing on all these downstream product synthesis processes. So based on our experience, we are developing technologies where we can use gasification to produce these downstream processes. So our portfolio includes several significant projects, such as the world's first IGCC plant using wood fuel, which is in Varnama, and also a 12 megawatt thermal oxy-steam demo plant, which is in Varkaus, the NSC biofuel. And these projects highlight our technical experience and successful track records in the developing and implementation of gasification solutions. So innovation, as I explained earlier, is at the heart of SFW. We hold over 500 patents across more than 50 families, primarily focused on fluid aspect technologies. And many of these patents contribute to global ecological goals. So to discuss more about the laboratory services which we offer in SFW is that we conduct extensive metallurgical, chemical, and field measurements to ensure reliability and to improve our technology's efficiencies. So we currently have now 4 manufacturing networks, with the largest one in China. So this is just to give you a brief overview of what SFW is and what we are as a company. Now let us turn our involvement. Let me discuss about our involvement in the FlexSNG project. So in this project, our primary focus is on the process design and techno-economics, and we are particularly focusing on the front-end process, that is the gasification plant. So one responsibility of SFW is that we are involved in the test campaigns, as discussed earlier by Sanna. So we participate in these test campaigns to share our experience and also to gain more knowledge from VTT and also these test campaigns, which has been really useful. And then the next responsibility of us is to scale up the processes and to perform techno-economic assessments. For this, the necessary modeling parameters and data are provided to us by a partner in CERT using Aspen Plus modeling. By using these data as a start, we scale up the process to a commercial scale. To explain in detail, we at SFW are involved in performing the basic design of the gasification plant, including necessary mass and energy balance calculations. Also, we are performing engineering tasks for biorefinery case, which is one of the case in FlexSNG. And we will be performing tasks such as mechanical design, PI flow sheets, and safety considerations. In addition to this, we'll also be performing CapEx and OpEx calculations for the gasification plant based on our experience and knowledge. That is all I had to say. And if you have any questions, please feel free to post in the Q&A. Thank you.
Thank you, Sri. That was really quick, very efficient presentation. So I welcome back on screen all of our presenters today. We have quite a few questions. I noticed that some of them have been responded to during the presentations, but there are still a few that we can open up to the presenters. So let's start with the first one. I think this one was answered during Sanna's presentation, but just to clarify, what is the gas conversion efficiency? Is there any?
So for maximized conversion of feedstock into syngas, the coal gas efficiency of the combination of gasification combined with catalytic reforming, that is in the range of 75–80%.
Great.
Yes.
Thanks for that. Another question here is about what the gas composition is. So what are you getting out in your syngas? I think, again, you mentioned that as well, Sanna, during your presentation.
Yeah, well, this time the presentation more focused on the how we could produce also biochar on the side. So I didn't actually present any of the main gas compounds. I don't know them by heart, but we can share some information maybe on the website or something afterwards. Maybe we have presented something in earlier public webinars or something. Yes.
Well, what we like to do is make a summary of all these questions, and then so for the audience, if you check on our website on this link now, I've just sent to everybody, we'll be publishing a recording of this webinar and responses to all the questions. So we'll get back to you on that one about the gas composition. There's a question here. What method are you employing for monitoring tars and benzene?
Yes, so maybe I can answer into that. So we utilize for the TARs the TAR protocol, and which also then contains the benzene measurement. And then we have also at our pilots, we have integrated micro GCs and special GC analyzers for semi-online analytics.
Perfect. Thanks, Ilkka. Thanks for that response. Wow, so many questions are coming in. We might not have time for all of them, but we'll see how we can get on. Another one here. Did you observe any agglomeration? I'm not sure. In the VTT gasification when you were feeding the straw?
Agglomeration, yes. So with in the first piloting runs that we conducted with the atmospheric pressure fluid aspect unit, we operated with straw feedstock up to, I think, a little over 830 degrees Celsius, and at those conditions we didn't see any signs of agglomeration. But then when we started the validation test campaign, we at the end of one of our test campaigns, we started feeding in straw, but the gasification temperature was, we were being maybe a little bit bold, and we were operating at gasification temperature of 850, 860 or something. And in those conditions and in pressurized conditions, then we could see some form of agglomeration, yes. But in the atmospheric pressure and lower temperature, we didn't have any issues.
Great, thanks for that, Sanna. Okay, so there really are a lot of questions coming in. So we'll see how far we can get. So I think this question's for Shri. It's talking about the plastic. So the question is about how to get plastic with syngas, but I think actually it's the other way, right? Syngas from plastic. Or
yeah, for plastic production, we particularly learn pyrolysis process, and from pyrolysis we utilize distillation process to separate the monomers and produce plastic from that. I hope Ilkka can answer more on this.
Yes, so of course, if you want to produce, for example, polyethylene, or so then there are processes through either methanol route or Fischer-Tropsch route to get into plastics.
Yeah, I can see the plastics becoming possibly the topic of the next research project.
That's very interesting topic, but not today.
Exactly. There's a lot to talk about with the plastics and plastic recycling. But good. That's a good intro into that topic there. We have a question here from Alberta. Have you any rough idea of the possible cost of the biochar obtained from this process? So we did have a webinar about biochar, and there was some conversation about costs, but I don't know if anyone here wants to talk about that today.
Yeah, the production cost of the biochar. This is something that the project consortium is currently working on. So the techno-economic assessment is now taking place based on the experimental data that we have received from piloting, and that is something that we will have at the end of the project. So we are not yet there. So, but it will be the figures will be then presented afterwards.
Perfect. So Sanna's message there is stay tuned and keep an eye on that website link, the FlexSNG news page. Good. Another question here from Juan, who says, I see that you're writing a response here about the energy balance. So is
yeah,
there
I
any
can say sure as well. So we have the initial mass and energy balance from Aspen Plus modeling, and currently we are working on scaling it up and performing the energy balance as for a commercial scale plant. So once it is done, I think we will be publishing it as in the dissemination of the project. So you could find it in the proceedings of the project. Yeah.
Brilliant. Perfect. So again, everybody, keep an eye on the news page for FlexSNG. Okay, so question here to Sanna from Thomas Hausman. Technical solution for biochar removal from bottom of BCFB reactor. How to handle condensing steam and escaping oxygen reacting with the biochar at the removal point.
Yeah, so well, the target was to remove the biochar from the bottom of the gasifier. So it's kind of the same method that we use for bottom ash removal, and then the batch of bottom ash is dropped in these containers that have that use nitrogen for inertization purposes. So that is kind of our basic scheme of bottom ash removal, and yeah. Ilkka, do you have any further comments on that question?
No, that was good, really good answer.
Perfect answer, Sanna. Good. Another question to Sanna. This is written here. Do you do in-bed fuel feeding or on-bed feeding in the BCFB reactor?
So in this case, the fuel was fed into the bubbling fluid dust bed, but the circulating the cyclone return leg that returns the charcoal on top of the denser BFB bed, bubbling bed.
Great, thanks. Now these questions are not specific. So what is the primary energy source considered? So that's open to the floor there. For the FlexSNG project, let's say.
Yeah, well, the primary energy source, you mean the feedstock basis that we are considering?
They haven't specified, so I guess it's up to you. You can talk about whichever.
At least the feedstock basis that we're considering is all types of biomass residues, like forest residues, but not really utilizing the virgin wood, but like barks and so forth, and as well as biogenic waste, so and agrobiomass, so all types of biomass residues and waste fractions are considered. Great.
And yeah, just to add to that, there will be case studies as part of this project. So again, remember to check back on the website. This project is finishing at the end of this year, so there should be more and more results as we go along the year. And okay, so some more questions here. What is the methanation process pressure? What is pressure of the methanation process?
Well, I think this is, well, we are working with our project partner, WIT. It's their methanation, Vesta methanation process. I'm not sure if they have actually disclosed it. I guess it was roughly maybe 20 bars. Ilkka, do you remember from any of the conversations?
Yeah, that's roughly, of course, in a way wood it's wood technology, but yeah, in a range of 20 bar.
Great, thanks. Okay, another one here. Be sure to vary the value of the steam in the steam if it has a source, or hold on, I'm a bit confused by the question. Okay, we'll come back to that one, Giovanni. Perhaps you can respond to that a bit clearer, because I'm not really sure what the question is. But no, we have another one. Do you observe any phenols or naphthalene as part of the tar components? And if so, are they completely converted?
Yes, in the raw gasification gas, there is definitely a lot of naphthalene and also phenols. But typically, if we achieve like a full conversion of tars, then all phenols and naphthalene will be converted. But if there is some leftover of tars, that's typically naphthalene, some small amounts. But again, that can be adjusted by the reformer design and selecting the proper operation parameters for the reformer. But typically, yes, they are converted.
Perfect. Okay, so I think there's reading Giovanni's questions. He's talking about the heavy metals that you find in the biochar. So have you found an increase in the biochars, in the heavy metals in the biochar?
This would be a good question to IFER, because they have been working with the biochar, analyzing the biochar, characterizing them in detail. So yeah. We at VTT, we have only been kind of supplying the material for IFER. So unfortunately, I don't have any good answer for that, but maybe we can ask someone from IFER.
Yeah, exactly. And I'd like again to remind Giovanni that the recording for the biochar webinar, which was early last month, is on the website. So perhaps you can check the recording, and if your answer to your question is not in the webinar, you can write to the presenters, or we can get that answer for you. Okay, so thank you so much for, I think that's all the questions answered. And we'd really like to thank you again for your participation, everybody's active participation, for our presenters, wonderful presentations, very clear and understandable. And I welcome you again to follow us on LinkedIn and the website on the news page. And there should be a final webinar after the summer, so we're talking around September time, in which we'll be presenting the case studies, and hopefully we'll be hearing from our Canadian partners and the students that have been studying from the Canadian side, the gasification process. So thank you again, and we'll see you after the summer for the final webinar. Thank you.
Yes, thank you.
Thank you all. Bye.